In the previous video, we've seen how we can find the electromotive force or the EMF induced when a rod is moved through in such a setup. A rod is moved through a uniform magnetic field in this direction. So we get some EMF, and if we complete the circuit, we can get a current flowing through it. Now let us assume that the wires that connect it have no or negligible resistance, and only this rod here has some substantial resistance, and let's name that resistance, call that resistance a small r. So that is the resistance of this rod here. Now we know that the EMF induced would be minus BLV, right? We've seen that in the previous video. I'll shift downwards to make it visible. Minus BLV. Perfect. Yeah. So now if I divide both sides by R, so remember, EMF divided by resistance, or rather potential difference divided by resistance, gives us current, right? Because V equals IR. So I've shifted R on the side. I get, so current equals potential difference divided by R, right? So what I can do is I can divide both sides by R, the resistance, and EMF divided by resistance is nothing but the current flowing through this through the whole loop. And because the resistance of the remaining part of the circuit is negligible, with the total resistance of the whole loop would be R, which is the resistance of this section, because the remaining wire has no negligible resistance. And if I divide this by R, I get current through the loop. So current through the loop is nothing but minus BLV upon R. And for now I'll just ignore this negative sign because it is only indicating the direction of the current, which we are not concerned with right now. Now we know that if we have a current carrying conductor in a magnetic field, that current carrying conductor feels a force, right? We've learned how to find the force on a current carrying conductor, the magnetic force, right? So we can calculate that even in this case. We know that the force on a current carrying conductor is simply given by ILB, right? Where I is the current through the ILB. Let me just confirm it. Yeah, so the force on a so this is separate, right? The force on a current carrying conductor is given by ILB. I is the current in the conductor, L is the length of the conductor, and B is the magnetic field through which the conductor is being in which the current conductor is present. Now what I can do is I can take the value of current from the above expression and put that in here. So what I get is force equals, instead of writing I can write this whole expression, BLV upon R times, I am left with LB. And to simplify, let me remove the stuff I have written up here. So you need to copy it side by side because I don't have enough space. I cannot fit all the complete derivation at once, so I need to remove stuff. Force equals, I can simply B into B square, L into L square. I have only one B, V, so only one V, and R in the denominator. So that is the thing that I'm left with after doing all the tam jam. And yeah, that is the force on this conductor. As I push it in that direction, I feel the force. Now let us just find the direction of the force that the conductor experiences. I can use again the cross product rule. So we know that the force in this case was ILB, right? And if I have to apply my cross product rule, it was actually IL cross B, and L is in the direction of the current. So what is the direction of the current in this case? Well, we figured that all the negative charges move towards this end, and all the positive charges had moved towards this end. So we get a current from positive side to the negative side, right? So the current was moving in this way, and so it was moving in that direction, positive to the negative side through the whole circuit. And back from this side to this side, right, in a loop. So we are getting a current in this side direction. So if it's I cross B, so what I can do is I can point my finger in the direction of current, and I can point my middle finger in the direction of the magnetic field downwards, and what I get is the force is in this direction, and so this means that the force is opposing the motion of the rod. So the force is in that direction. I was pushing the rod in that direction with the external agent was pushing the rod in that direction, and the force due to the magnetic field was in that direction. So this magnetic field is trying to oppose the motion of the rod, and that is in accordance with Lenz's law, which states that the current would be induced in such a way so as to oppose the change in flux. So it is opposing the change in flux by stopping the rod from moving further, right? And that is the force on this particular rod. Now what I can do is I can also find the power that I am producing by pushing this rod in that direction. How do I do that? Well, first we need to find the work done in this case by the external agent as it pushes the rod in that direction. What is the work done? Well, work is simply force times distance. So I'll just find a small amount of work done. So what is that small amount of work done? dW, or let's say I move the rod from this position to this position. I just displace it slightly, like a small displacement, dx, let's call that dx. And so by doing a small displacement dx, I do some small work dw, and to find that work dw, what I do is I multiply the force that I'm applying, that the constant force that I need to apply, times the small distance that I move, dx, right? Let's say this small distance is that dx, just convert this dx, yeah. So now what is the force? This thing is the force, so I can say dw equals b square l square v upon r dot dx, or multiplied by dx, right? Now what I can do is I can differentiate, or rather divide both sides by dt, or the time taken for me to move this rod by the small distance dx, or in other words I am differentiating both sides with respect to t. For all those people who understand in differentiation nicely, for those I can say that I am differentiating both the sides with respect to time, or in simpler words I am simply dividing both sides by the small amount of time that I take to move it. So let's say I move it 1 centimeter, and to move it that 1 centimeter, let's say I take 0.01 seconds. So dw is the small work that I do, maybe 0.01 joules, and dt is that small amount of time that I take to perform this work, let's say 0.01 seconds, and dt is again that 0.01 seconds. Dx is that 1 centimeter that I move. Now what is dx by dt? That small distance divided by the small time is the velocity at which the rod is being pushed, and in mathematical terms I can say that dx by dt is nothing but the derivative of distance, which is velocity. So I can write that as v. I hope that fits. Yeah. And what is dw by dt? What is the rate of change of work, or rate of doing work? It's power, right? Work divided by the small amount of work divided by the small amount of time taken to do that work is power, or the rate of doing work, dw by dt, is power. So I can replace this whole term with the letter p, or power. So this is the power that I'm providing, or the power that I am using to move this rod in that direction, and that is equal to b square l square v into v upon r, and v into v can be written as v square, and what I'm left with is b square l square v square upon r, and this expression here gives me the power that I am putting into the system by pushing the rod in that direction. And just for completeness sake, let me leave this expression here, or let me write the expression here, p just to remember the expression, P equals B square L square V square upon R. So this is the expression that I have. Sorry, I need to remove you. B square L square B square L square V square upon R, that is the power that I am putting into the system. And now, just for completeness sake, now a question that arises is, where is this power going? Where is all the work that I am doing? Where is all that work going? Obviously, because there is some current in the whole loop, there is some heat generated in the loop, and that heat generated, it is a constant. The heat is constantly being generated, and that is where the energy that I am providing, that is where it is going. And yeah, so let us just find the power that is being released, or that is being used as the rod heats up. So what is the power that I'm getting out in the form of heat energy, or rather what is the rate at which heat is being released by the rod? So we know that power in a circuit is given by P equals IV, or in other words, I can also write this as P equals I square R, right? I can replace the V equals IR, so I times IR, or I square R. So P equals I square R. I hope you remember this expression from class 10 and earlier studies. So P equals I square R. Now again, if we recall the term for I have forgotten it, let me look it up. I had figured out that current would be BLV upon R. BLV upon R. This was the expression for current that I had got. So I can use this expression for current, I can put in here, and I can get the value for power. Power equals I square, which means BLV upon R. This is current, this is I, so I square times R, and if I open all this up, I get P equals B square L, that is a square, B square L square V square upon R square times R. I can cancel this square with this R, so I'm left with only R, the single R there. And if you notice, P equals B square L square V square upon R is the same expression as this expression. And yeah, I've got the same expression, which simply states that the power that so what is this power? This is the power that I need to spend, or I need to put into the system to move this rod in that direction. And what is this power? This power is the rate at which heat is being released. So this power is the rate at which work is being done by me or by the external agent to push this rod in that direction. This is the power at which, or this is the power that tells me the rate at which heat is being released, or the ohmic loss, or the ohmic heat that is being generated in this particular rod, in this particular setup. And because both expressions are exactly same, that indicates that the power that I put into the system is equal to the power that I get out of the system. And so the work that I put into the system, the rate at which work is being put into the system is equal to the rate at which heat is being released, or energy is being released by the system. And that is perfectly in accordance with the law of conservation of energy. And yeah, that is it for this video. And yeah, that also explains why Lenz's law works that way. And yeah, that's it for this video.